Now this is the first demo that we will see in the exception handling section, and the code that we will use is more or less the same as what we have been using so far. So there will be slight changes to the same code to demo different aspects of the microcontroller. So here we have a separate project created called exception handling, under which we have these files. That is, in the root directory of exception handling, we have build example main.c, core initialization header file. Exception handling examples is something that we are not going to use. These are some files that we are not going to use. And we have the linker file. When we go into the source file, we have the core initialization C file, the startup file, and the include has the memory map. So this is what we saw previously. That is the memory map, the core initialization, startup, so on and so forth. So we are using the same file structure, but our intention in this demo is to explain the non-floating point enabled stacking process for Cortex-M4, especially on the STM32F411 processor. So let's get started. Now, this is some code that you had seen in the linker makefile chapter segment. So it's not that relevant in our case here when we are looking at interrupts. And this is also pretty much the same code that we saw. We will not talk about the SysTick interrupt in this particular demo. We will be talking about the SysTick interrupt in a later demo in this segment only. So we do a PLL initialization to begin with, of course, and the PLL initialization in the clock tree will come later in a later chapter, where we will study in detail how this happens. In this line, we initialize the floating point unit, and now there is something interesting that is going on here, and we will see that floating point unit. So the stacking mechanism that we will see now will be through the mechanism of lazy stacking, and we will not disable the floating point unit for a particular reason, which I will tell you later. So we will have the floating point unit enabled, and what we will do here is we will comment this line out and save the file, and we will have lazy stacking demonstrated. So what we do is we first set a breakpoint here in this line 33 in the main. So this is the build example.c file, build example main.c file. Okay, so we set a breakpoint here, and we set another breakpoint in the SysTick handler. So the breakpoint is already set, so we set another breakpoint in the SysTick handler. So the intention of doing this is we will come to explaining the SysTick handler later. Let's assume now that we have a handler which is fired when we run the code. So this is a typical interrupt service routine, and we have been talking about interrupt service routines. We have been going through the slides, and we have been talking about interrupt service routines. But so for now, just assume that this is an interrupt service routine. That's it. Okay, how and where it is, how it is written is something that we shall see later. Let us cover the stacking first, because it's very important, and we'll have to pay very close attention to understand the whole process, because it is one of the most complex aspects of the processor. So let's put the code to debug we have seen previously also how to put the code in debug. So just I have the board connected, of course. So the board is connected and the board is up. So I'm just putting the code in debug right now. So it finishes one round of compiling and now it connects to the target. Once it connects to the target, we can see that the control is here. That is this variable. So what we'll do now is we'll do a free run because we've set a breakpoint here. So we'll do a free run and we'll come up to here. And one more thing, I do understand that many of you will not be aware of working on the GDB debugger directly. Not to worry, we will be using a limited set of commands, GDB commands. And I personally feel that this is the easier way to explain the stack rather than having to go through and have a look at the GUI here, because in the GUI again we'll have to see the disassembly. So we'll have to look at the disassembly, we'll have to look at the code, and we'll look at the stack here. We could do it through memory view as well, but I feel this is a better way of doing it, and we get to learn a little bit about how GDB works also. And of course, everything that we are doing here, single stepping and breakpoint, everything is actually it is actually GDB that is working in the background, right? And what we are doing here is we are directly giving in GDB commands. So we could type continue here, or we could press this. Either way, it is going to. So let's type C, which is continue, and we see that the control has reached this part. Now this is just assigning the value of this value to the variable. So there is no floating point operation here. This is some value that is stored somewhere in the flash, and this value is just being brought into this variable. That's all. Okay, so we will really not have anything. We'll not see anything here as such. And now let's do a free run again, and hopefully the SysTick interrupt will get triggered, and we will see that the program will halt at the SysTick interrupt. Now let us do a few things here before I forget. We'll have to make a note of a few things. That is, let us first make a note of what is the stack pointer here. So we'll check the stack pointer value, which can be done here through the registers. You have the registers here. You can check the stack pointer through here, which is this 20002B8C. But let us do it through the debugger. So we keep the disassembly window here, and then we check what the stack pointer value is. So we do P and $sp. So this actually gives you the current stack pointer value, that is 2B8C. Now we saw the same stack pointer value previously also. So what we'll do is, for now, we'll just note down that value here. So let's note down the value. So this stack pointer value is 0x 2000 to B8C. Okay, now I'm noting the stack pointer value here is because once the program moves away from this point in the code, the stack pointer value will change, of course, right? So that is the reason I'm keeping this stack pointer value saved, and we will see in later how this affects, how this changes, and what is the size of this. We'll calculate the size of the stack from there. Okay, so now let's continue. If we continue, I hope that it is going to hit the breakpoint. That is the breakpoint on the SysTick handler. Thankfully, it has come and hit the breakpoint on the SysTick handler. here, and it is in the core initialization file. So it has come to this file now. So it is in this file now, core initialization stm32 f411xe.c. Okay, so we have the sysdig handler here. It has come and it has hit the breakpoint here. Now let us see a few things here. Okay, we will demo this thing. We'll talk about this thing later also, but now this is the sysdig handler function, and in assembly we have come here. This is the sysdig handler function. If you can see, it has gotten into the function, but this is what the compiler has added here. It has done a push R7 LR. Okay, so it has pushed two registers R7 and LR onto the stack, and we are here right now. That is, we are at a branch instruction here, because we have to branch to the toggle LED function. Okay, now let us see what is the current stack pointer, and then we will study the stack. So let's see. We do a print stack pointer here again. Now we see that the new stack pointer value is 2000 2B60 here. Okay, so let us write down the value of the new stack pointer also. So the stack pointer, new stack pointer here is 0x2000 to B60. So how much has the stack pointer moved by? So we'll have to, so whatever amount that stack pointer has moved by is the size of the current stack. So what is the size of the stack? The size of the stack is SP minus SP new. Now I'm subtracting the new from the old, because the stack is a descending stack. That is the reason I'm doing this. It is not an ascending stack. Ascending stack would mean I would have to do SP new minus SP. New would be a higher number. But in this case, since it's a descending stack, it is SP minus SP new. And we can see that the SP value is bigger than the SP new value. So let's subtract 2000 2B8C minus 2000 2B60. So if you subtract this, I've already tried it out before, but nevertheless let's do it once again. So just opened up the calculator, and let's try to see what value this gives us. So 2B8C minus 2B60. So 2B8C minus 2B60. Okay. So the value is 2C. 2C is 44. Okay. So let's write down the value 44 here. So it's equal to, let's rub this out. It's equal to 2C, that is in hex, which is equal to 44. So 44 means how many words? So 44 means 44 by 4, because one word, so the address advances by one word here in the case of Cortex M4. So the how many words do we have? We have 11 words here. Okay, so this is 44. The value is 44, so we have 11 words. 11 words means 44 bytes. Now let us print the stack from the current stack pointer, which is the current value, and let us print 11 words from the current stack pointer. Let us do that. So we'll go to the debugger. So please pay close attention to this. This is important. So we do x 11x. So x11x just means that print 11 address locations from the current stack pointer. So we get something like this. Okay. Now there is a lot of information here. These two, whatever you see, are the top of the stack. Okay, because these have been saved in the end. So 2002 2B8C and this number is something that we have spoken of, that is 7Fs and a 9. That is what Cortex M4 automatically filled into the link register, and here the compiler has saved the R7 which actually had the stack pointer and the link register onto the stack. So we have this value. So let us see what this value means. And so FFFF9 here, if you see this, FFFF9 means, sorry about the clutter, it's return to thread mode. So this is an instruction to return to thread mode. Exception return uses non-floating point state from MSP execution and uses the main stack pointer after return. So what we see here is, rightly, it is the stack size is only is much smaller, and it is using the non-floating point mode. So that is why you see 7Fs and a 9. So we will see this value change when it uses the floating point mode. Now, since this is, so we have to discount these two values, right? Because they have been put after we have come here. So after the stack was entered, 2 more pushes had been done. So our actual stack that is saved by the controller, that is the Cortex M4 processor, that is by the hardware itself, is this region. So let us go through each register or each memory location and talk about what these are. Okay, so let's have a look at the registers first. This would have changed. Okay, so this would have or may have changed, but nevertheless, let's hope that the registers did not change, at least the first 4 registers. And let us go back to the presentation ones to have a look at what the stack looks like. So if we discount those 2 pushes that was done inside this SysTick ISR function, we see that R0 is saved first, R1 then R2, R3, and then R12, R14 return address and XPSR. Okay, so ideally this should be R0 at this address location. Okay, so it is 606468. 68 is going to have R0. So just have a look. R0 is this value, and this value is saved here in R0. R1 is 6 again, so 6 is saved. Thankfully, actually what we should have done is, and what you should do is, before the jump was made, before the continue was made and we came to the SysTick handler, we should have ideally made a note of all the registers that are to be saved here, these registers, so that it is easier for you to compare when you come into the SysTick handler, that is the ISR. So you need to be careful about that. Then R1, as we see, So this is R1. This has to be R2, of course. So this is the value of R2. So R2 is this. So R2 value is 2B70. That is R2 address location is 2B70. R3 is again 41BE3712. So this is R3. Now what is after R3? We have R12, R14 return address. Now these would have changed. These would have definitely changed. So let's see. So we have R12 after this. So let's see what R12 has. R12 has 0. We have 0 here, but we don't know. We don't know. This may have changed, but this is where the R12 is saved. So let's have a look. This is where the R12 is saved. This location. So R0, R1, R2, R3, and then R12 here. So we are actually going through the stack in real time. Okay, that is the stack without floating point. Okay, so R0, R1, R2. So what comes next? R14. R14 was what? So R12, R13, R14 was the link register. Okay, now this is the previous link register. So when we jumped from main to this ISR, this was the link register contents. Now the link register has changed, as you can see here. This was the link register content before it jumped to the main. Okay, what comes next? You have the return address and the XPSR. So we have the return address. So this was the address from where the program or the code jumped to the ISR. This address 80001DC. So this is the return address. So this is all done by Cortex M4. These two, of course, were done by the compiler in code. These are all automatically done by Cortex M4. And what is the last one? It is the XPSR. So this is the XPSR value. XPSR. Okay. So again, the XPSR value is going to change here. Now, before we start talking about the double word padding for the stack frame caused by an interrupt in Cortex M4, let us briefly understand what an alignment is. Now, you would be aware of what an alignment is, but nevertheless, let us just do a recap. So if you have some address which is byte aligned means the address can end in anything. For example, if you have a 8-bit controller, the address is byte aligned because the instruction access is 1 byte. Right? So it is always aligned because it's 1 byte alignment. Half word alignment means 2 bytes. So if you have a 16-bit processor, suppose, and you have address locations like this, so half word aligned would mean the binary address, the lowest binary digit for the address always has to be 0. Okay, so so the addresses will be, so if the address starts from 0, it is going to be 0, 2, 4, 6, and so on. For a word alignment, the addresses, the bottom 2 addresses have to be, or the bottom 2 bits of the address have to be 0, 0. So it has to start from 0 and then go to 4, then 8, then 12. That is 4 bytes, 8 bytes, 12 bytes. So this is called word aligned addressing. Okay, so it jumps. So the addressing will look like as we said, 0, 4, 8, 12. So in hex it is going to be 0, 0x4, 8, and then 12 is going to be C. Okay, and then 16 is going to be 1, 0, and so on. So this is how the addressing will progress in the case of a word aligned address location. Okay. So this address location is called word aligned, and for a 32-bit controller it is always easier and faster to access word aligned boundaries. If the content within the memory is word aligned, it is much easier and faster for the processor to access it. Now, double word aligned means the last 3 bits of the address is 0. So it's 1000. So the addressing starts like this. It starts from 0 and goes to 8, and then goes to 12, then goes to 20, 24, and then 32, and so on. So it's the 8 times. It just, it's a table of 8. So 8 ones, 8 8 twos. Sorry, sorry about that. I forgot my table of 8. So 0, 8, 16, 24, 32, and so on. So now let us see what this looks like in hexadecimal. So let's open the calculator. So this is what the last addresses are going to look like. So if you open the calculator, it is like this. So you have 0. So 0 plus 8 is going to be, in hexadecimal it's going to be 8, and then if you add 8 to that, it is going to be 10 in hex. Okay, that is 10. 10 in hex is 16 in decimal. Then if you do plus 8, it's going to be 18. Then plus 8, it's going to be 20. So this is how the addresses will progress. Okay, then if you do plus 8, it's going to be 28, plus 8, it's going to be 30. So I have kept these numbers here just to show you something important. So let's keep the calculator open and let's have these numbers here. Now we will go to the code. Now so far, whatever we had been seeing, that is the stack that we studied, had a extra in its stack frame, and we really didn't look into it. I just went ahead with the explanation and demo with the stack frame with padding. So the stack frame had a word of padding actually. Now so if you are trying it out here, there's a concept of double word padding in the case of ARM Cortex-M4 architecture. Now, double word padding is essentially when your stack is not double word. So when your previous stack pointer ends in a location which is not double word address, the next stack pointer information is double word padded. For example, if you have a stack which is ending with a non-double word value, so say it ends with a non-double word value here. So this is your stack, and say the stack grows in this direction. Okay, of course this is the increasing address. Stack grows in the downwards direction, and this is non-aligned, so it's not aligned to double word boundary. If that is the case, then the Cortex processor adds an alignment padding and then starts the stack. So your final stack will have an element or have a word extra mostly, and that is what you see in the case of that is what you just saw. That is, you had that extra padding which made the stack 9 bytes, that is rather than 8 bytes. So when you are getting into a debug, you might see this happen, and this is not always the case. So if the stack alignment is to a double word, you will see that this is not happening. So when you are inspecting or investigating your stack, you'll see sometimes you are getting an extra extra word in the stack, and sometimes not. Happens with both stacks without floating point and with floating point. Like we saw in the previous case, our stack was 44 bytes, and that 44 bytes, that was 11 words. But I thought that let us have another demo on this as to how to control. So this is not useful for you in regular programming, but if you have to understand the padding, this is going to help you out. And this double word padding feature can also be disabled. So we will disable the double word feature padding also, and we will see how the stacking behaves. So we'll see both. So now there's a trick that I had to play with the code in order to have it misaligned so that a double word padding gets added sometimes. So this is something that you have to do. So I have added a ASM command to just increase the stack pointer here. Now this is again conditional. That is, when you get into the debug, first time you get into the debug, if you see that the stack is not aligned, like we saw previously, the stack was not aligned. Now this is a fresh compile I have done, and I observed that this time the alignment is proper. So it is somehow double word aligned, and I was not seeing that extra padding in the stack area. So keep this instruction handy if you're inspecting the stack. Depending on whether or not the stack is double word aligned, you may comment this out or you may not comment this out. Okay, so let's keep this commented to begin with. And let's put the code in debug, and we'll see what we're talking about. We'll put a breakpoint in the sysdig handler like before, so that it comes in the breakpoint, it comes and halts at the breakpoint. So now what we'll do is we'll put it on debug. So we have commented out the assembly instruction, and let's now see how the code behaves. We'll have to keep an eye on the stack pointer, of course, and we will also study the stack frame through GDB. So now let's come here. So let's see what the stack pointer says. So the stack pointer is 2B90. Okay, so 2B90, this is actually double word aligned. Okay, so when you say, so if for you to quickly check if it's double word aligned, so 90 is in hex is, again, just a moment, 90 in hex happens to be your 144. Okay, so let's divide 144 by 8. So 8 ones are 8, 9, 10, 11, 12, 13, 14, 8 8s are 64. Okay, so 18. So this is divisible by 8. So this is already double word aligned. If this is double word aligned, we will not see the padding because it is already it is already doing what the Cortex-M intends it to do. So when we jump now from, so let's jump to the sysdig. When we jump to the sysdig, we see that the stack pointer value is 2B68. So 2B68 is, so 2B68, so 90 minus 68. So we did all this before previously. We'll get 40. If you remember previously we were getting 44. Okay, so 4 less because this is already aligned. This did not add up padding. So if you go to the debugger console, so now the stack length is 10 words, right? So 2B68 and 2B90, right? So this was previously, it was 0x 200 2B90 minus 0x2000 2B68. Okay, and that gives you 40 decimal. Okay, so if it's 40 decimal, it is 10 places. The stack is 10 places. So let us print the stack now. So we will do x and 10x, and so the stack size is 10 words now. Sorry about that. X10x and $sp. The stack is 10 words, and of course when you look at the disassembly and when we look at the assembly code here, out of which 2 are previously pushed, so your stack starts from here and it ends here. So this is where your XPSR is stored. So let's have a look at the XPSR. Now this is important. So when you look at the XPSR value, the stacked XPSR value, this is the stacked XPSR value. Okay, now the stacked XPSR value, look at the 10th bit or bit number 9 of the XPSR value. You will see the bit number 9 here is 0. So bit 9 means, bit 9 does not mean 9th bit, it means the bit number 10, that is bit 0 to bit 9. If we consider it that way, bit number 9 is 0 here in this. So when the stack unwinds and you go back to the previous stack, this value is actually checked by the controller and it knows whether it was padded or not padded, this value. Okay, so that is how it knows whether it's, so depending on that it rolls back the stack pointer that many bytes. Now what basically happens is, if you have to so this is one part of the mechanism. Now the problem is, if you have to make the stack forcefully out of alignment, generally what happens is sometimes it goes out of alignment and sometimes it doesn't, and that is not that much within your control. That is the way you write your code. The stack may or may not go out of alignment. So if, and moreover what happens is, whatever you put in the main, all the variables, the local variables that you put in the main, generally so let's put it on debug and show you that what I mean. Generally the compiler is intelligent and it will assign a double word aligned stack in most cases. That is what I had observed. So see, sub sp 16, so 16 is a double word aligned. So I may not be entirely true in saying this, because this stack pointer that you see, the initial stack pointer, if this was again not double word aligned, so this stack pointer is definitely double word aligned, which is why when 16 is deducted from this, it is again still on a double word boundary. But had this stack, that is the stack pointer that was prior to the main, that is when it was in the startup, and from there the main was called, and that stack was not double word aligned, then if you add 16 to that, this will also not be double word aligned. So this is what it is. So if say your previous to main stack pointer is not double word aligned, say it ends with something like 0c, Okay, so C is not double word aligned. Then if you add 16 uh, 16 bytes to that, so then what happens is, that is, if you subtract, that is, subtracting means you're adding to the stack, because the stack is a decreasing stack, goes down in the case of Cortex. So if this was not aligned, then this will not be aligned. But in our case, not probably, in our case, the previous stack pointer is also aligned, which is why we are this is in alignment. Sometimes, depending on the code that you have in the startup GCC, this will go out of alignment. So this will go out of alignment because of this calculation. Now, once that happens, how do you put it out of alignment? Because if you add some variable here, the compiler will adjust the stack pointer in such a way that it is generally double word aligned. Say it will probably play tricks with you. It'll not let you move the stack out of alignment. So for that, what you do is you keep instructions like the .asm instruction that I showed you here. This is, the compiler will not suspect this as a push. It will just take it as an assembly instruction. It will not know what this instruction is going to do. So you can fool the compiler, and you can nevertheless move this stack out of alignment. So let's do that. So let's have this. So I'm just uncommenting this. Okay. So now what is going to happen is, let's put a breakpoint here, and we'll stop this. And then let's start the debug again. When we start the debug and we hit this breakpoint, we'll see something interesting happening. Now it starts and comes here. Let's see what the stack pointer is now. The stack pointer is 2B90. So this is double word aligned. So obviously we will not be able to see the padding in this code. But if we run this instruction, so let's single step. We run this instruction, say. So we do a step over. See what happens to the stack. It becomes 2B8C. The moment it becomes 2B8C, it is not double word aligned. So now this stack pointer is moved from a double word alignment. So when that happens, when we move to the systic interrupt, we will see it behave differently. So the stack size is going to be different. So let's move into the systic. Now let's take the stack pointer size. Okay, so 2B8C, and then this is going to be 2B60. Oh, okay, so 8C minus 60. Let's calculate what the value is. So 8C minus 60. It is, can you see this? It is 44, like the way we got previously. Interesting. So what it has done is, it has detected the word alignment is, it's not double word aligned, and it has added a padding bit. So let's study the stack now. Of course, if we study the stack, we'll see a padding has been added there. So this doesn't say much, but anyway, x, now it is 11x. If we want to see the padding, but then again, we're just seeing an extra memory, that's all. So now this is the padding that has been added. And one more interesting thing, the XPSR, the stored XPSR is here now. So this is the padding, and this is the XPSR. Okay, now the 10th bit, or the bit number 9, is 1. Can you see that? This is very important. So when the stack rolls back and goes back to the main, the Cortex-M knows that this has been word padded. So it rolls back the stack pointer to compensate for this padding. Okay. Now this is the AAPCS standard. Now what if somebody did not want this alignment. Now, as per the AAPCA standard, we don't have the control to change the registers that get into the stack. That is what the interrupts do. But we definitely have a control over whether we want this double word alignment or not. So let's stop the debugging here. What we need to do in that case is, there is in the CCR SCP, in the CCR register, there is a mask. So let's look into the CCR register now. Okay, this is the configuration and control register. Okay, it's the SCB. So system control block, it has a configuration and control register, and this is the stack align bit. That is the bit number 9, means 10th bit. Now, if this bit is made as 0, it becomes 4-byte aligned. It is by default 8-byte aligned. That is why even just after startup also, we are seeing this double word alignment happening. So we'll do one thing. We'll just disable this, or we'll make it 4-byte aligned, and we will run the same code and we will see what happens. We'll see the stack size. So now this is the double word padding disabled. So we are just making that bit from 1 to 0 in that CCR, and that's, since it's bit number 9, we are just shifting it left by 1, and then we are ANDing it, and we are making that bit 0. So this bit is made 0 now. This bit is made from 1 to 0. So in the main, what we'll do is, we'll uncomment this. So now it disables the double word padding, and we'll see what happens. So now let's put it for debug again. So we debug, and then we come here. We see the stack pointer 2B90. We go one step further, and the stack pointer becomes 2B8C. So 2B8C means it is out of alignment. Now I repeat, mind it, when you are trying it out, sometimes you will see that the double word alignment is, and the stack, this will be automatically out of double word alignment, and you need not use this. So do it accordingly. Okay, adapt to how the stack is getting organized in your case. Now it is 2B8C. Now let's jump to the handler. Now when we jump to the handler, we see the stack pointer as 2B64. It was 60 previously. So when we subtract now 8C minus 64, 8C minus 64, we get 40. That is 10 words. So let's see the stack now. We'll have X 10X now, because it's 10X and $SP. So this is what you see. Now you have the 9th bit as 0. That means this is not double word aligned. That is, the padding is not done. The padding is not done because we have disabled it through the API here. We have disabled the double word padding here. So even if it is not double word aligned, it will ignore that, and it will keep the stack from keep the stack word aligned. Okay. So this is something very important you need to understand, because when you are studying the stack, when you are single stepping through and you're checking the memory and all that, you might get confused as to why the stack size is sometimes it is 10 words and sometimes it is 11 words, and this is the reason why that happens. Okay, now we will see one more thing, which is also very interesting and very important. And don't think that this is not because of this being an interrupt handler. It is not the case. Whenever, in the case, any compiler, especially GNU compiler, whenever, and we talked about it in the presentation also. So whenever the GNU compiler gets into an ISR or any function for that matter, and if that function calls another function, the return from that function to the caller function is done by pop R7PC. That is pop R7PC. It is here you have a push R7LR. So whatever you have in the LR is moved to the PC. See this LR PC. So the link register has to be the contents of the link register has to be moved to the PC, right? So there are different ways of doing it. Okay, there is a conventional way and there is this way. So whenever there is a function call within a function, the compiler uses this method. Now the beauty of ARM Cortex programming is that this is treated as a normal function. So the Cortex hardware does the hard work of doing all the stacking and then creating a value like this. So the compiler is oblivious to what is really happening. It just loads the link register contents back into the program counter, and seeing that value in the program counter, the controller automatically knows that this is an interrupt return. So it assumes that the current stack that it is working on is a stack that has been created by the interrupt. So you can actually corrupt the program if you load this kind of a value into the PC by any chance. So be careful. You could because this value, whenever this value is seen by the controller assumes blindly that it is a return from interrupt, any value like this. So you can corrupt the controller, fool the controller into believing that it is going back from an interrupt if you put a value like this into the program counter, and it will fault. It will try to go back to some memory location, which thinking that it will take a content of a memory in the stack pointer, which is not a memory address, because it thinks that it is going back, and then it will probably go back and hit some wrong place. It will not be able to access anything from there, that region, and it will probably fault. It will probably throw a memory access fault and so on. So this is how the stacking happens in the case of non-floating point applications. Now let us return from this interrupt. Okay, so when we return from this interrupt, let us single step now, because we have not set a breakpoint, or rather we could actually set a breakpoint here. Let us set a breakpoint in the while loop now, because it has to return and come back here. So let us set a breakpoint in the while loop. We may or may not set a breakpoint. Of course, it is going to get stuck in the while loop, but let us do that. Let us do a continue here and see where it goes. And then we will see what the stack pointer value is. So let us continue. And as expected, it comes and gets stuck in the while loop. That is, it has come out of the interrupt, and we are not letting the interrupt fire again, because we've just trapped the control here. Now let's do this. Let's just erase this and see where we are. So we just check the stack pointer now. Okay, so print the stack pointer. And we see that we have come back to the old place, that is 2B8C. The old stack pointer contents may be retained, but all that process has taken place in the backend, right? Since the register contents did not change, you may not realize, but then all these registers have been restored and all the values have been set back to what it should have been. So the stack pointer is restored, everything is restored, and XPSR, all these values in yellow have changed now. the link register value 80001D5, if you remember. This was the previous value. All have been changed. Everything has been restored to where it was, as if nothing happened. All the process. So a great deal of load was taken up by the controller itself, and it saved all the registers. All that the compiler did was to save 2 registers, thus increasing the size of the stack by 2. We saw that the stack size is actually 9 instead of 8, and we saw the registers, or we checked that the register values that were saved on the stack, and we returned from the stack here in the while loop. So this ends the demo for stacking and unstacking for non-floating point scenario. Next we will see stacking and unstacking for floating point scenario, which is pretty much the same, except the fact that the stack is going to be much bigger this time, about 27 words. Let us see a couple of more scenarios. Now, this time, what we'll do is, in the same SysTick handler ISR, we will comment out the toggle LED call. Save this, and we will now try to do a debug in the same way as we do. And we will see some difference in the compiled disassembly code, which I want to show you. So let's put this on debug as we did previously. Okay. So now it's again in the main, and let us comment this out. No, this is fine, sorry. So we have not uncommented the actual floating point instruction, so this is fine. Let us come up to here, like do a continue, or this time, so just to show you that it works both ways. Previously we typed a C here to continue, else we can click here, that is resume, or we can press F8. So there are multiple ways of doing the same thing. So let's resume, and we will come here. Now let's continue again, and we will hit the, we hope to hit the ISR. Now as you can see, the ISR here, it's the toggle LED is commented out, it has come into the memory barrier instruction. Now checking the disassembly out, if you see this one, check this one out. So the push and the pop in the SysTick handler is different now. It has just pushed the R7, which is the link register, and it is popping the value and it is returning. So previously we saw a pop instruction. Here we see BXLR, which is the conventional assembly instruction to return from this, and this has been done because the LR has not been stomped over. The LR is retained, so that it can be, the BXLR can be done this way rather than doing a pop of 2 values that we saw previously. This is one scenario. I want to show you another scenario which is also pretty interesting. So let's stop the debug, or let's stop the debug because we need to recompile. And now let us comment out this initialize floating point unit. So what's going to happen now? Our floating point is not going to be initialized in hardware. So the code will run, but will not have any the floating point unit will be off. Let's see what happens. So we will follow the same steps as previously, but this time the execution is going to be different. So we are on debug. 1 comes here, 2 it goes here, and then it keeps hitting the SysTick handler. That's okay. Now what I wanted to show didn't happen here because I committed a mistake. So this is also interesting rather than so we learned something new here. This is the actual floating point instruction. That is, if this instruction is executed, only then will the floating point instruction in assembly be executed. If we had not come here, the floating point instruction would not have been executed, and what I was trying to show you would not happen. Okay, so let's try the code again now. Let's save it and try the code again now and see what happens. So we will try the same thing again. We will resume. It hits this breakpoint, and then we resume again, and somehow we see that the control has gone somewhere else. We don't see the control anywhere here. It's the code is running, or the code is stuck somewhere. So let's pause the program or suspend the program and see where it is. So we see that in the startup file, it has got stuck in the hard fault handler. The fault ISR is the hard fault handler here. So this is the hard fault handler. So it has got stuck in the hard fault handler. So what happened? Why did we get a hard fault here? We are trying to use the of course you can guess the reason. We have disabled the floating point unit and we have done a floating point operation. So what is the floating point operation that we have done? The floating point operation is we will reset the program again, and we'll come to this breakpoint, and this is the floating point operation VLDR S15R74. Okay, and we adding. So it's a multiply by 2, and these are the instructions, floating point instructions that are written by the compiler to perform this particular task or perform this particular action. But we don't have the floating point unit enabled, and that is why it went into a hard fault. So let us have a look at the make file. So we previously also we saw that we had enabled mhardfloat here and mpfu as v4, which is why the compiler is coding in this floating point instructions, because it knows that this processor is using a floating point unit. Let's try an experiment and see if by removing the floating point unit here, that code after disabling that floating point instruction, keeping the floating point instruction disabled, whether the code is going to work or not. Just let's try it out. So what we're going to do is we'll keep the GCC options as it is. We'll just copy this here just to save the original command, and we will just remove this mhard float and the float mpfu instruction, and we'll comment this out. Let us see if it compiles or not. I'm not sure if this is going to compile. So what we have done is we have told the compiler not to assume that there is a floating point unit here. So we've just left that part out, and let's see if this code compiles. So let us put it on debug, where it is going to again compile the code. So it says nothing to be done for all. Let's clean it up now. Let's clean up the code. So it says nothing to be done for all because the code is already, the output files are already existing. So let us just clean this up so that the debugger is the compiler is forced to pick up the makefile. So let's run it now. It should, it'll pick this up, and what we'll see now is the compilation would have gone through, and let us see what assembly code has been written here. So let's step, and now you can see that the entire float start to instructions are completely different. LDR, move, you don't have the same instructions as previously. So now if you jump, it goes to the SysTick handler. Interesting, because now the compiler has compiled code which is not depending on the floating point. So now even if you did an initialize FPU here, it wouldn't matter if the FPU is floating point unit is initialized or not. The compiler is going to anyway ignore, or it will not code for the floating point unit. So this is an interesting observation that we made here. So let's restore the old GCC options, because we need the floating point, because the floating point unit makes the calculations much faster, and we need to also verify the stack with the floating point unit enabled. So that is the next thing that we are going to see.